In this video, we're going to take a look at section 5.6 on applications, which is just another way of saying word problems. There are three different types of word problems in 5.6. So we're going to do an example of each of them, and then we'll have a few more examples at the end that I'm going to encourage you to try first before I do them. But the first kind of problem that you will encounter in this section are work problems. The formula for a work problem is W equals RT. It kind of works the same as the distance formula, D equals RT. These variables kind of mean the same thing. So R is a speed. It's how fast you work. How fast the work is done, maybe is a better way to put it. How fast the work is done. So it's a rate. T is the time, how long you're working for. And W is the amount of work that you would accomplish given those two numbers. All right. Something I want to point out, I'm going to try something a little bit different than I normally do. And I haven't taught this in my face-to-face class yet. We're going to be doing that in a couple of days. And I think I'm going to try it in that class as well. So I just want to point this out now because it'll be relevant when we do this problem. That if you solve this formula for R by dividing T to the other side, you get that R is equal to W over T. So keep that in mind, that the rate, how fast you work, is equal to the amount of work you get done divided by how long it took, the amount of time. All right, so R is equal to W over T. All right, so let's take a look at an example. John can cut and split a cord of firewood in 6 fewer hours than Dwight can. When they work together, it takes them 4 hours. How long would it take each of them to do the job alone? All right, so even though the formula itself is fairly simple, W equals RT, it's going to apply to actually 3 different things in this problem. John, Dwight, and I guess, well, let's just say it just applies to 2 things. I mean, I was going to say, and them working together, but we're going to kind of deal with that. I don't know how to say it conceptually. It's going to be the thing we deal with directly, but it'll get split into how much work is John doing, how much work is Dwight doing. So I think we just need to worry about 2 things here. So John and Dwight. Because it applies to 2 different things, we should use a table to organize the information. We talked about this earlier in the course as well, right? So if you have one formula, but it applies to more than one thing, a table is a very helpful way of organizing all the information and trying to fit it all together. So let's draw a table. And because the formula will apply to 2 things, we'll make 2 rows, right? So we'll have, and I'll just use their first initial here. So John and Dwight. So we'll have a row for John and a row for Dwight. And we'll make a column for each variable in the formula. So we build the formula into the table. So we have R, we have T, we have W. All right. And this table, this is where the together part comes in. So they're going to be working together on this particular day. That's what this table is for. This table is for the situation where they're working together. So that's what I meant by, we're going to consider that as well, but it's going to be the overall thing that we're focusing on. So now we want to go back through the problem and fill in what we know. And this is where students have a little bit of trouble because, for example, the most direct piece of information here is that when they work together, it takes them 4 hours, right? So actually, this is fine, right? So when they work together, it takes them 4 hours. So that means they're working together, John and Dwight, side by side for 4 complete hours. So how long is John working when they're working together? It'll be for the 4 hours, right? He's going to be working 4 hours along with Dwight, who's also working the same 4 hours. So they're both putting in 4 hours of work. Right, so you don't have to split the time up and say, 2 hours for John, 2 hours for Dwight, or anything like that. It's like when you go to work and you clock in, and your coworker also clocks in. You're both working that same amount of time, right? John's working the 4 hours, and Dwight's working the 4 hours. All right. So what we need to figure out is the speed here. So this problem is a little bit different than what I was expecting. I'm sorry. I was going to make a certain point, and then I ended up not really making it because it didn't really apply here. I guess I could still make the point, which is students will look at this and see the 6 fewer hours and think, oh, this is the time. And I jumped to this, which kind of eliminated that possibility. But this isn't for the time. So the reason they're telling us that John can do the job in 6 fewer hours than Dwight is not so that we have the time for this problem. It's so that we have the speed. Because knowing that John gets the job done in 6 fewer hours tells me that John is faster at the job. His work speed is quicker than Dwight's, so that he gets the job done sooner. So when they tell you the time for the individual people, that's so you know their speed, so you know who's faster and who's slower. And you can quantify the speed. And the way you do that is what I was referring to earlier, right? You have W equals RT, that's the formula. So when John's working alone, let's not do John, let's do Dwight actually. So when Dwight's working alone, the problem is we don't know the time, right? So when Dwight's working alone, how long does it take him to do the job? We don't know. And we have no information about that, right? They at least give us a clue about John. He gets the job done in 6 fewer hours than Dwight. But Dwight, they don't give us any information about at all. So we're going to let X represent how long it would take Dwight to get the job done by himself, right? And so if we plug that in here, so if it's just Dwight working by himself, we don't need a table. We have just Dwight working by himself. And the time it would take Dwight to get the job done by himself is X hours, right? We're going to call it X. The speed we don't know. That's what we're going to try to find out. And of course, we don't know the time either, but the speed is what we're trying to identify here for use in this table. Because the assumption we're making is that Dwight would work just as fast whether he's working by himself or working with John. Right? His speed, his work speed is not going to change in either case. Now, in reality, that might not be the case, right? Maybe Dwight works faster when he's working alone, but then he slows down when he's working with John because he's busy talking or whatever. But we're assuming the work speed stays the same regardless of the situation. Now, how much work is Dwight getting done in 1 hour? We have to put a number here for this, right? We can't say, oh, it's a cord of firewood gets done, right? We can't write that word here. That's not going to make sense mathematically. So the way we quantify the amount of work that's getting done, if Dwight is completing the entire job in that X hours, is we say that's one job getting done. And so we really don't care what the job actually is. We're not going to put any units on that. It's just one job is complete in that X hours. And now we can solve this for R by dividing X to the other side. And that gives us his speed, which I said I was going to do things differently, but this is really what I do every semester. But that's exactly what we mentioned over here, right? That somebody's speed is the amount of work they get done, which in this case is 1 cord of firewood getting chopped, over the time it takes them to do that job, which for Dwight, we don't know, so we're calling that X. So I think I probably should have stuck with this. I think that would have been easier, right? So for Dwight, his speed is 1 over X. All right, whoops, going the wrong direction. All right. So that's what we're going to put for Dwight's speed. It's 1 over X. And once you see the pattern, you don't need to do this every single time. The pattern is the speed for each person will be 1 over how long it takes them to do the job by themselves. So for John, it takes him 6 fewer hours. So John's speed when he's working alone, John's time, I should say, when he's working alone, is 6 less than Dwight's. It's going to be 6 less than X, which means we want to subtract. But it's not going to be 6 minus X. You got to be careful about that. So 6 fewer means you start with X hours, and then you're going to take 6 less than that. And so it's X minus 6. And it's very important when you're subtracting that you do that in the right order. Otherwise, the math doesn't work out. Right? So think of it this way. If I wanted 6 fewer than 10, 6 fewer than 10 would be 4, right? 6 fewer than 10 or 6 less than 10 would be 4. And the way you're getting that is you take 10 minus 6. So you start with the whole, the how do you want to say, the total amount first, and then you take 6 off of that. And so it's going to be X minus 6. I hope I'm explaining that okay. I'm gesturing with my hands, but you can't see me doing that. So I don't know if that would help with the explanation. Either way, the thing you should come up with for John's speed is 1 over his time, which will be X minus 6. Right, now that we have a speed for John and a speed for Dwight, and we have the time, we can now use the formula to fill in the last column for W. We take R times T. So for each person, for John, we're going to take R times T. So it's going to be 1 over X minus 6 times 4. That'll be John's work, right? So not only, I mean, it's not just, we're not just multiplying two things together randomly and getting some random result. I mean, this has something, it means something, right? If you take a speed times a time, the result you get is the work. And so this expression represents the work that John is getting done. We'll do the same thing for Dwight. We'll get 1 over x times 4, and that'll tell me Dwight's work, that he's contributing to the job. Now, we could probably write this a little bit nicer than I did by multiplying these together. Think of this as 4 over 1. Multiply this into a single fraction. So this will be 4 on top and then x minus 6 on the bottom. Right? So that's John's work. We'll do the same thing here. Think of this as 4 over 1. We get 1 times 4 on top and then x times 1 on the bottom, which will just be x. So that's Dwight's work. What do we know about the work that they're doing together? Well, together, the work that John does combined with the work that Dwight does, they should get one job done. They should get 1 quart of firewood chopped up, right? And so we're going to take the work that John's doing, which is 4 over x minus 6, add that to the work that Dwight is doing, which is going to be 4 over x, and that should add up to 1 job being completed. And so that'll be my equation. And that's how every work problem equation gets set up. You take the work from each individual, add it together, and set it equal to 1. And now you can see why this word problem didn't show up earlier in the course, because look at the type of equation we're getting. It is a rational equation, like we were studying a few sections ago in section 5.5. And we have to solve this equation. So we're going to do that the way we learned in section 5.5, which is the first step is to find the LCM, which means we take each factor that occurs here. X minus 6 is one factor. X is a different factor, right? These are different from each other, so each of them has to be in the LCM. And then we multiply that LCM to both sides of the equation. So see if I can make enough room here for this. So we're going to take x minus 6. Oh, sorry. It's already starting to mess up on me here. Okay. X minus 6 times x. And then we will distribute it to both sides of the equation. Even though there's no fraction on the right-hand side, you have to multiply it to both sides of the equation. Think of it as being over 1. When this gets multiplied to the first fraction, the x minus 6's are going to cancel out, and I'll have 4 times x left over. Right, and so we'll have 4x left over from the first term, plus a fresh copy of this gets multiplied to the second fraction. The x's are going to cancel out, and so we will have 4 times x minus 6 left over. Right. So we'll have 4 times x minus 6 left over, and we'll keep that in parentheses, equals, this gets multiplied to 1. So we don't really even want to think of it as a fraction for that. It's going to be x minus 6 times x times 1, which means it'll just stay the same. X minus 6 times x. All right, and so this is the equation we come up with that now doesn't have any fractions, so now we can solve that equation. Let me switch to a new page because it's already having trouble keeping up with my writing, and we're not going to have enough room here to solve it anyway. So see if I always mess this up. Okay, let me try that again. Let me cross that out. Let's try one more time. I'm going to go a little bit bigger here. Okay. All right. There we go. And we'll put this on a new page. All right. So we want to solve this equation. All right. And we'll start by distributing the 4 into the parentheses and distributing the x into the parentheses here. So we'll get 4x plus 4x minus 24 equals x squared minus 6x. So we have a quadratic equation. We'll go ahead and combine these together. We get 8x minus 24 equals x squared minus 6x. It's still x squared, so to solve a quadratic equation, we want to get 0 on one side, and I think it'll be better. I don't want to make the x squared negative, so I'm going to get 0 on the left-hand side by subtracting the 8x over to the right-hand side and adding the 24 to the right-hand side. And so we'll get 0 over here equals x squared minus 14x plus 24. So we want to factor this by finding two numbers that multiply to 24, add to negative 14. That's going to be negative 12 and negative 2. Right? Negative 12 times negative 2 is 24. Negative 12 plus negative 2 is negative 14. You set each factor equal to 0, and you end up getting these answers. X equals 12 and x equals 2. So you get two solutions. So you might say, wait a minute, how can there be two right answers here? And there's not two right answers. So if you were to assume 2 as the correct answer, then remember x is representing the amount of time that Dwight takes to do the job by himself. So if we assume the answer for Dwight is it's 2 hours for Dwight to get the job done by himself, how long would it take for John to get the job done by himself? Well, remember, John's time was 6 fewer hours than Dwight's. So if I were to take that information to John's time, I get a nonsense answer. I'll get 2 minus 6, which means John gets the job done in negative 4 hours when he's working alone. And that doesn't make sense, right? So that can't be the right answer, so we have to throw that one out. It must be this one. Dwight takes 12 hours to do the job by himself, I don't know why I'm having trouble talking, which means that John takes 6 fewer hours than that. 12 minus 6 means John would take 6 hours to do the job. And that's what we would type into Math Excel. So Dwight takes 12 hours, John takes 6 hours to do the job when they're working alone. All right, so sorry that problem took so long. This one I can guarantee will not take quite as long. These are proportion problems. A proportion is what you get when you set two ratios equal to one another. So this is one ratio, A over B, and this is another ratio, C over D, and we're setting them equal to each other, which means you can cross multiply to solve this type of equation. So there's some word problems where that's exactly what you want to do. There's two ratios that you're going to find in the problem that you're going to want to set equal to each other, and then you solve the proportion once you get it set up. So let's go ahead and take a look at a word problem that has a proportion. To determine the number of trout in a lake, a conservationist catches 183 trout, tags them, and throws them back into the lake. Later, 45 trout are caught. 15 of them are tagged. How many trout would the conservationist expect to be in the lake? So this is something that I've always wondered about when you read these stats from these, wildlife agencies that say, oh, the wild population of this animal is blank. And I always wondered how in the world would they even have an idea of what that could be? I mean, they're not out there counting every single animal, I assume. And so this actually gives you an idea of the way that kind of number is estimated. You do a proportion. By tagging, sorry, I choked on my water a little bit. By tagging, now I lost my train of thought. You tag some of the animals in the wild, let them loose, let them mix back in with the general population. And then, all right, I'm sorry about that. I wanted to start over this problem, but my recording software doesn't let me go back to a previous point. And so I'm just going to leave it in because I don't want to start over from the beginning. So, all right. So we are going to set up two proportions here. So what I was mentioning was conservationists will tag a certain number of animals, let them mix back into the general population, and then capture some animals later, either on camera or, like in this case with fish, I assume like actually grabbing them out of the water, and then seeing of the ones they're catching, how many are tagged. And that gives them a proportion that they can apply to the general population since they know how many are tagged altogether in the general population. So the ratios that we want to set up here are the number of tagged fish over the total number. All right. And so we're going to start with the second piece of information, that they caught 45 trout and 15 of them are tagged. So I think this one's a little more obvious, the order that ratio should get set up in. All right, so we'll go ahead and do it over here. So, oh gosh, okay, let me try that again. Okay, so on top we'll put the number of tagged fish, which I think is pretty obvious. It's 15. On the bottom we'll put the total number of fish that were caught, which is 45. And so that's a ratio, right? 15 tagged fish out of 45 fish that were caught altogether. We want to do the same thing with this first number. We have 183 fish that are tagged out of the general population, the entire general population, which we don't know, which we're calling X. So how many trout do we expect to be in the lake altogether? We're calling that X. We don't know what that is. That's what we're trying to estimate. So the ratio here, what's going to go on top, it might surprise you, is the 183. A lot of students, their instinct tells them to put that on the bottom, because I think what we've learned previously when we've done problems like this, when you set up a ratio like this, it's small number on top, big number on the bottom, right? We don't really pay attention to what the numbers are representing. So when you see 183, you think, oh, that's kind of a big number. I'm going to put it on the bottom because the big number goes on the bottom. But this is actually the small number in this case, right? It's the number of tagged fish out of the general population, which will be bigger than that, right? So 183, you want to pay attention to what that number is representing. It's the number of tagged fish. Tagged fish are going on top. The number of fish in the general population, that's the total number. That's going to go on the bottom. And we're going to assume that these ratios are equal. Now, they might not be exactly equal, but they should be pretty close, especially if they gave it enough time for those fish to mix back in with the general population. They get a sample later of 45 fish, however many are tagged. That should give you a good idea of what the ratio is for the general population. So they should roughly be equal to each other. So we're going to set them equal to each other. And we're going to solve this equation. It's a pretty simple equation, and we can cross multiply, which makes it even easier, right? So we get 15 times x, which will be 15x. We'll have 45 times 183. I knew this was coming up because I did this problem with my class on just the other day. And I said, I need to make sure I have a calculator handy, and I didn't make sure to have one handy. So let me get my phone here. I'm going to do it in just a second. Sorry. So we have 45 times 183. It's going to be 8,235. 8,235. And then we set those equal to each other. Right? Now we'll solve for x by dividing 15 on both sides. And I was surprised because I thought, oh, this isn't going to work out nice, but it actually does. So divide by 15, and we get 549. All right, and so that would be how many trout we would estimate to be in the lake. So again, it's an estimate. It's not an exact figure, but gives you a rough idea of how many are in the lake. All right, so that's how proportion problems work. Sorry about all the glitches and getting through that problem. Hopefully we won't have any for this. So here is a familiar type of problem. So the first two that we just did, we hadn't seen before in this class. But this one, we've done uniform motion problems before, but there's going to be a twist on these that make them a little bit more difficult to do. So I'm not going to go through this. You know what these letters mean. You should know what they mean. R is the speed, T is the time, D is the distance. I'm not going to write it down. All right. So the speed of a stream is 4 miles per hour. A boat travels 5 miles upstream. Now notice that's a distance, 5 miles. They're giving us a distance. That's what makes these problems a little more difficult. The boat travels 5 miles upstream in the same time it takes to travel 13 miles downstream. What is the speed of the boat in still water if there was no current, right? So this stream has a current. So what I like to do is draw a picture. All right, so here's the river. The current, let's say it's going in this direction, right? It's flowing down. All right, so it's going in this direction. And we have a boat, right? So we have a boat, let's say it's starting down here for the first situation. So this is my boat, right? The speed of the water is 4 miles per hour. The boat, when it travels upstream, it's heading against the current, right? Upstream means going against the current. And so the current's pushing back on it at a speed of 4 miles per hour. So it will get slowed down by 4 miles per hour, right? And it's only able to travel 5 miles in this situation. So it's going to go upstream. It can only go 5 miles in the same amount of time that if it was going downstream with the current, it would actually go much further. It's going to go 13 miles, right? And both of these take place in the same amount of time, right? So in the same time. All right, so that's the situation. We want to find the speed of the boat on its own, right? Without the water's help. And so we'll call that x, because obviously we don't know what that is. That's what we're looking for. So how fast is the boat going? It's going x miles per hour on its own. And then the current's pushing against it when we go upstream. It's pushing it along when we're going downstream, right? So, but the speed of the boat is going to be x miles per hour. So D equals RT is the formula that applies to this situation, but we have two different scenarios, right? Upstream and downstream. So we're going to make a table to organize all this information. All right, and so we'll have one row for upstream, one row for downstream. We'll make a column for each variable in the formula. So we have R, we have T, we have D. All right, so we'll fill in what we know. And what we know most directly about this problem is the distance. The distance traveled upstream is 5 miles. So I'm going to go ahead and put that here for the distance. So this is a little bit weird because normally we're filling in the first two columns and then multiplying those together to get the last column, but that will not be the case for this problem. So we know the last column, the distance. I keep wanting to say the speed for some reason. The distance is 5, and for downstream, the distance traveled will be 13 miles. Right? And so the next thing I would recommend filling in is the speed. Right? The boat going upstream, the boat itself is going X miles per hour, but it's getting slowed down by the stream that's going 4 miles per hour. So the net speed of the boat in that situation will be X, how fast the boat goes on its own, minus 4 because the water's slowing it down by 4 miles per hour. The speed downstream, I think you probably can catch on to this pattern. The boat itself would be going X miles per hour on its own, but it's getting a boost from the current of 4 miles per hour. So the net speed of the boat downstream will be X plus 4 miles per hour. And that leaves the time column as the empty column that we need to fill in using this information. And so we have to sort of reverse engineer. Knowing the distance and the speed, how can we use that information to fill in the time? And so you think about the formula, D equals RT. If I want to know the time based on the distance and the speed, let's solve the formula for T by dividing R on both sides. Right? And so we'll get that the time is the distance divided by the speed. Right? So for each row, we will take the distance from that row divided by the speed for that row, and that will tell us the time. And so for going upstream, we'll take the distance, which is 5, divided by the speed, which is X minus 4. All right, so this is what we're using to find the time. So to find the time, it's the distance divided by the speed. I'm sorry I keep misspeaking. Hopefully you're able to follow along still. For downstream, the distance is 13, divided by the speed, which is X plus 4. All right, and so now we have an expression that represents the time it takes to go upstream. We have an expression that represents the time it takes to go downstream. And if you remember, I made a big deal about it earlier, that it will take the same amount of time for either one, right? It's the trip going upstream is the same time, takes the same amount of time as the trip going downstream. So these times should be the same. And so we will set them equal to each other in this problem. So we'll have 5 over X minus 4 equals 13 over X plus 4. Right? That'll be the equation. This is a nice equation to get because we can solve it by cross multiplying, right? So it's 1 fraction equals 1 fraction. We'll get 5 times X plus 4 equals X minus 4 times 13. So again, we multiply the opposite corners together, set the results equal to each other, and then we solve for X. So we'll distribute the 5. We'll get 5X plus 20 equals, we'll distribute the 13, and we'll get 13X minus, I know this one off the top of my head because I think of a deck of cards, right? There's 4 suits in a deck of cards, and each suit has 13 cards, and I know the total number of cards in a deck is 52. Right? So that's how I'm figuring that out. And we want to solve this equation. I was going to try to squeeze it in here, but I just feel like it's going to be too much of a hassle. So let me copy this over to a new page. All right, and we'll finish it over there. All right. So this is a linear equation, so we don't have to get 0 on one side and factor. What we want to do in this case is just get x on one side of the equation. So I will subtract the 5x. Sorry, let's try that again. Whoops, I hit the wrong button. Oh no, I went way back. Okay, sorry. I confused the undo button with the previous page button because they're both arrows pointing to the left, so I apologize for that. I'll just have to erase it now. Okay. All right, So we're going to subtract. I want to keep x positive. That's why I'm doing it this way. Subtract 5x over to the right-hand side. So we'll have 20 equals 8x minus 52. And then we'll add the 52 over to the left-hand side to get x by itself. And so we're going to get 72, which is kind of a nice number to see with the 8 being here. And so we will divide by 8 on both sides, and we get a nice answer. We're going to get x is equal to 9. And that's the answer, the final answer to the problem, which is how fast is the boat on its own. That's what x was representing. So the boat would go 9 miles per hour on its own without the current affecting it. All right, that's the speed of the boat in still water as they were describing it. All right, so that's an example. That's one example of each type of problem that you will see in section 5.6. There's work problems, there's proportion problems, and then there's these distance problems, these uniform motion problems. All right, so I have a few more examples here, but they are, going over the types of problems that we already talked about. So there's one more of each type. And so for each of these, I'm going to recommend that you pause the video, give the problem a try yourself, see how far you can get with it. It's okay if you can't complete the problem, but just see what you can do with that problem, and then resume the video so you can kind of check to see if you were making the right choices, if you were, adequately progressing through the problem as you should. All right, so let's take a look at this problem. A swimming pool can be filled in 17 hours if water enters through a pipe alone, or in 20 hours if water enters through a hose alone. If water is entering through both the pipe and the hose, how long will it take to fill the pool? All right, so there's two things involved here getting this work done. All right, we have a pipe filling a pool up, and we have a hose filling a pool up. And so we'll make a row for each of those. And the things we're looking for in this problem are R times T, R, T, and W, right? And R times T does equal W. And this one still kind of works the same way. We want to fill in the first two columns, multiply those together to fill in the last column, and then from there we can get our equation. So remember what we talked about earlier. We're being told here that the swimming pool can be filled in 17 hours through the pipe, 20 hours through just the hose, right? So these are if they were working alone. If the pipe was working on its own, it would take 17 hours. If the hose was working on its own, it would take 20 hours. Even though that looks like it's a time, and it is, right? 20 hours is a time. That information is being provided to tell us the speed of each of these things, right? So remember we talked about when we did this problem earlier that the speed for the pipe would be 1 over the time it would take to do the job alone. And so if the pipe takes 17 hours alone, then the speed for the pipe is 1 over 17, right? It's the amount of work the pipe is doing, which is one job, divided by the time it would take to do the job, which is 17 hours. So that's the speed for the pipe. The speed for the hose is going to be 1 over 20, right? And the time it's going to take for them working together. So remember, this table is for when they're working together. We're being asked that, right? We don't actually know. We don't know how long it's going to take. That's what we want to find out. So we're going to call that X. So the pipe will be working for X hours, and the hose will be working for X hours. Because again, they're working together side by side at the same time. They're both putting in the same amount of time, right? So now that we have the first two columns filled in, we'll multiply those together. We'll get X over 17 here. So think of this as X over 1. So this time I'll just go ahead and multiply them together right away instead of doing it later. Same thing here. Think of this as X over 1. When you multiply these fractions together, you get X over 20. And so remember what these represent. This is the amount of work that the pipe is contributing to filling up the pool. This is the amount of work that the hose is contributing to filling up the pool. If I take the work they're doing and combine them together, they should get one job done. One pool should get filled up. And so the equation is going to be X over 17 plus X over 20, right? That's the work the pipe contributes plus the work the hose is contributing. Together, they will get one job done. And so that's the equation we need to solve. So this one's not quite as bad as the first one that we looked at, except the numbers are not that great. To solve this equation, we're going to follow the same steps that we did earlier. We want to find the LCM. And the LCM of 17 and 20, especially when the numbers are this big, I don't know, this might not be the least common multiple, but I still think it'll be the easiest common multiple, if you want to think of it that way, is just to multiply the two numbers together. 17 times 20 is 340. Right? Let's just have that be our common denominator. It might not be the least common denominator, but it'll get the job done. Right? So maybe I'll cross out the L. This might not be the least common denominator, but it is a common denominator that we can use. So we'll multiply 340 to the whole equation, right? And we'll distribute. Remember, 340 is just 17 times 20. So if you think of it that way, this is 17 times 20. When I multiply this to the first fraction, the 17s are going to cancel out, and I'll have a 20 left over, right? Or you could just do it in your calculator. 340 divided by 17 gives you 20. And then you have an x here, right? So what's going to happen is the 17s are going to cancel out. And so what's going to be left over is x times 20, right? Which will be 20x. Plus, when this gets multiplied to the second fraction, the 20s are going to cancel out, and we'll have 17 times x left over. Equals, this gets multiplied to the right-hand side, even though there's no fraction there. 340 times 1 is just going to be 340. And so for this case, I don't want to think of it as 17 times 20, since there's nothing to cancel out. I'll just think of it as 340. All right. Then we will add these together. These are like terms, so we're going to get 37x equals 340. And then we'll solve for x by dividing 37 on both sides. Sorry, it doesn't fit there quite that well. And so we get, I don't think this divides nicely. We get 340 divided by 37. So I'll do this on my calculator on my phone. And we get not a very nice answer here. We get 9.189 ... And so I don't know how we might want to type the answer in here for Math Excel, since it doesn't say how much to round. And I thought it might ask for how many hours, how many minutes. It will sometimes do that, but I don't see a minutes here. So I think what we should do is not write it as a decimal. It's not a very helpful number as far as figuring out, well, how long do I have to wait for this pool to fill up? But I think this is what you'd want to type in. Right? Just type it in like that as a fraction. That's an exact answer. And so it'd be exactly 340 over 37 hours, whatever that is, which is 9.189 ... So it's about 9 hours that it would take for the pool to fill up. But since it doesn't ask us to round it, I don't think it wants a decimal answer. It wants the fraction answer. And I don't think that can be reduced. Trying to think. Yeah, I'm pretty sure that can't be reduced. Because 37 is a prime number, and 37 doesn't go into that. So I'm pretty sure that's the right answer. All right, let's move on to the next example. The ratio of the weight of an object on Mars to the weight of an object on Earth is 0.4 to 1. How much will a 139-pound astronaut weigh on Mars? All right, so pause the video, see if you can figure this problem out, and then resume the video to check your progress. So this one is a proportion problem. I mean, it starts off with the word ratio. So what you want to do is set up two ratios and then set them equal to each other. The first ratio, I think, is pretty obvious here. It's 0.4 to 1. So we're going to set that ratio up as a fraction. So it'll be, well, it doesn't matter which one goes on top or which one goes on the bottom, but I'll just go in the order that the numbers are given to me. Now, it doesn't really matter the order that you put these in, which one goes on top and which one goes on the bottom, for the first fraction, as long as you do the same order for the second fraction. That's where it becomes important. So we really do need to make a note of what's the order I'm putting these numbers in. So this is the weight of an object on Mars to the weight of an object on Earth. So the Mars weight is going on top, the Earth weight is going on the bottom. So we want to make sure we keep the same order when we set up the second ratio. How much will a 139-pound astronaut weigh on Mars? So this is their weight on Earth, and we want to know how much are they going to weigh on Mars. So when I set up my second ratio, the 139 should go in the denominator. Right? That's the weight on Earth. Earth is in the denominator. The weight on Mars goes on top. We don't know what that is, so we will call that x. I will give it, since it's an unknown value, we'll use a variable to represent that. And then we're going to set these ratios equal to each other, so now we have a proportion to solve. Right? And so again, we can cross multiply, so I'll have 0.4. Now this one says round to the nearest tenth, so this one will be rounding. We'll keep it in decimal form. We'll have 0.4 times 139, which will be 55.6. And then we'll have, this one's nice and easy, 1 times x, which will just be x. And we set those equal to each other, and that gives me my answer right away. So it's 55.6. We didn't even have to round. It was already to the nearest tenth, all right? Or it was already to the tenths place, so we don't have to round it off. Okay, one more example to look at. A steamboat travels 6 kilometers per hour faster than a freighter. The steamboat travels 147 kilometers in the same time the freighter travels 129 kilometers. Find the speed of each boat. So pause the video, give this problem a try, see what you can do with it, and then resume the video to see if you are on the right track. All right, so this one, again, we're going to set up a table because there's two things involved here. We have the steamboat, which I'm going to call S, and the freighter, which I'll call F. All right, we'll make a column for each thing in each variable. I say each thing, that's really generic. Each variable in the formula, R, T, and D. All right, and we'll set it up in this order. But what's going to happen, just like the last problem we did of this type, they're giving us the distances. The steamboat's traveling 147 kilometers. That's the distance for the steamboat. The freighter's traveling 129 kilometers. And then we're going to fill in the speed. The steamboat travels 6 kilometers per hour faster than the freighter. So sometimes students will say, oh, the speed of the steamboat is 6. It's not 6. It's 6 faster than whatever the freighter's speed is. So we need to use variables here. The one we know the least about is the freighter speed, so I'll call that x. So I'll put x here for the speed of the freighter. The steamboat is 6 faster than that. So whatever the speed of the freighter is, the steamboat's going to go 6 kilometers per hour faster than that. So the steamboat speed will be x plus 6. And just like we did before, to fill in the time column, we will have to take the distance and the speed to figure that out. And we saw this in the last example. The time is the distance divided by the speed. So that's how we will fill in the time column here. We'll take the distance, which in the case of the steamboat is 147, divided by its speed, which is x plus 6. For the freighter, we'll take the distance, which is 129, divided by its speed, which is x. And then we will make an equation out of this. And what we're told, just like the last problem, I don't know if this will happen every time, but for these two examples, it happened to be the case. The times are the same, right? So these two boats make these trips in the same amount of time, so the time should be equal to each other. So we'll get 147 over x plus 6 equals 129 over x. And then we want to solve this equation. Again, it's one fraction equals one fraction, so we can solve it by cross multiplying. So we'll get 147x equals 129 times x plus 6. So I'm going to put the x plus 6 in parentheses, and I just like to put the number in front of the parentheses. I know I didn't do that last time because I wanted to keep the order the same. X plus 6 times 129, but I prefer to put the number in front of the parentheses when that happens. But either way is fine. Either way, the next step will be distribute the 129. So we'll get 147x equals 129x plus, oh, again, I need a calculator. Should have planned ahead to have that handy. So give me a second. We'll have 129 times 6, which will be 774. All right. Then what we'll do, I think I can squeeze this down here at the bottom. We're going to subtract the 129x over to the left-hand side, because we're going to get x on one side of the equation, everything else to the other side, because it's a linear equation. And so this is going to be, well, let's see if I can do this without my calculator. 17 minus 9 would be 8. And then we borrowed a 1 from that, so it would be 18, right? 3 minus 2 would be 18. Equals 774. And then to solve for x, we'll divide by 18 on both sides. All right. And so I still have the 774 in my calculator, so I can just divide by 18, and I'll get x is equal to 43. So again, what was x representing? Go back to your table. X is the speed of the freighter. So the speed of the freighter would be 43. We'll go ahead and type that in here. And then the speed of the steamboat, sorry, this was the freighter speed. If I can spell it right. The speed of the steamboat is 6 more than that. So I'll just add 6 to this to get the speed of the steamboat, which will be 49 kilometers per hour. So after you answer for the speed of the freighter, it's going to give you another prompt for the speed of the steamboat. And for that, you'll type in 49. All right, so that concludes the video on section 5.6 on applications.